Oh, good day, everyone. This is Alan Clegg from ISC, and today we are going to be starting with the very first of our DNSSEC webinar series. We're going to be doing about 10 weeks, one per week, 1 hour per week of information on DNSSEC. This is information that is taken from classes that I've previously taught and presentations that I've previously made. I'm very glad to see you and have you all here today. So thank you very much for attending. I am not able to see the chat, but if you do have any issues, please feel free to put a message there, and either Vicky or Suzanne will be able to help you out, hopefully as necessary. So the list here shows the topics that are going to be covered each week. So today we're going to be talking about the DNS threats and the need for DNSSEC. This is not going to be purely DNSSEC. It's also going to be a couple of other threat mechanisms, but that's what we're going to talk about today. And then you can read the others there. I highly recommend, obviously all of these. It's a very good and intense class. It actually is done as either a 2-day class or as part of the 5-day DNS Unbind class. If you do take this as a class, there are labs. We will not be doing any labs during this presentation, during these 10 weeks. But if you are interested in that, that is available. We can get you additional information as we go. So today we're going to talk about, as I said, the DNS threats. We're going to talk about spoofing. We're going to talk about the denial of service issues. We're going to talk about some name server vulnerabilities, and we're also going to talk about registrar hacks. Each of these presentations, let me back up a little bit, I apologize. Each of these presentations is going to be about an hour long, possibly a little bit less than an hour, possibly a little bit more. I realize that makes it really hard for people to plan, be around for an hour, but the plan is to be as close to an hour long per session as we can get. We will see as we go on, though, how that works out, and we will make adjustments as needed. So talking about DNS spoofing, there are a number of different mechanisms of spoofing. There are triggered cache poisonings, and I'm going to be giving examples of each of these. There is message ID guessing and query prediction. We have man-in-the-middle attacks. They're betrayal by a trusted server, where you know that somebody out there is giving you an answer and you assume that it's correct, but somebody has made sure that it is not. And then we're going to talk a little bit about the distributed denial of service using open recursive servers as amplifiers. So the first of these attacks that I'm going to talk about was done back in July of 1997. And this was Eugene Kashpureff. He was an activist within the network community, and he recognized that there was a flaw in the way that a certain piece of the infrastructure was implemented. And he was able to use that as a lever to make his activism a little bit more visible. So in July of 97, he used a direct triggered cache poisoning attack against the InterNIC's website. So if you were around back in 97, or if you remember the network history from back then, there was a large, there was a groundswell of people that said, we don't need a centralized DNS. We need, a distributed route. We need to be able to, be more of our own boss than have somebody tell us how this DNS thing is going to work. And so Eugene looked again at the DNS protocol and saw a little flaw in the way that some of the servers dealt with information in the additional section of the DNS answer. So the way that this attack was done, you'll see that we have an evil resolver on the left. We have the ISP's recursive server on the right. We have the InterNIC.net authoritative server, and that's who the user is actually wanting to get the answer from. And then we have the unsuspecting user down in the bottom right-hand corner. So the way that this attack initially was started was that the person doing the attack, the person actually attacking the unsuspecting person, would do a request for this InterNIC.net address record. So you notice that this is the InterNIC.net is not the InterNIC website. This is not the InterNIC site that the end user was actually wanting to go to, but it was an alternate site and an alternate address record. So from the outside, this evil resolver person would send that query to the ISP recursive server. Now, this recursive server is the server that is being used by whoever is the target of the attack. So the query was made, and obviously the ISP recursive server to make the attack work, it didn't have any information in the cache. So it sent out and it did a query for InterNIC.net. So it would go out to the .net or to the root servers, then to net, and then to InterNIC, and it would eventually end up at these authoritative servers for InterNIC.net. And again, this is exactly what should occur in the protocol by the recursive server at the ISP is doing exactly what it should be doing. Now, the InterNIC.net site, the authoritative DNS server, was running modified code, and the modification was something that instead of returning a standard response for the address record for www.InterNIC.net, it would respond with an answer that, yes, it has the A record for InterNIC.net, but it would also contain in the additional section a response or a record that gave the address record for InterNIC.net. So InterNIC.net was the site that Eugene was trying to get people away from. So when he would respond with these modified resource records, with these modified packets, in the authoritative, or in the answer, in the additional section, there was information that really had absolutely nothing to do with the query that was asked. You notice that the iterative query was for www.InterNIC.net, but the response was including a bogus entry for InterNIC.net. So when this response came back, the ISP's recursive server said, okay, that's wonderful. Thank you very much for the information. And it put all of the information into cache. So at this point, it cached the address record for www.InterNIC.net, but it also cached the response for www.InterNIC.net. And at this point, the cache was poisoned. So at any time someone would go in and do a query for www.InterNIC.net, they would get back the response that Eugene had created and not one for the recursive server would not end up going out to the authoritative server for InterNIC.net. It would use the information that it had received from the modified server at InterNIC. So now the unsuspecting resolver says, hey, my user wants to go out to InterNIC.net. They are going to get back the information from the cache that was the incorrect information. And at that point, the bogus response is going to go to the unsuspecting user. Now, this was a very interesting attack because by modifying the cache information or by poisoning the cache in the ISP's recursive server, you were basically giving back incorrect information to anyone that used that recursive server. And you could basically control the length of time that that information was in cache, because since you were responding with the A record for www.internic.net, you were able to set the TTL on that record. You were probably unable to guess exactly when the unsuspecting user was going to go out and do the query, but you could set either a very long TTL to make the information stay in cache for longer and catch, more people, or just do it once to catch a number of people over a longer length of time, or you could do it for a very short length of time in which case anybody that was looking to see if modified information was in the cache, unless they were looking during the period of that shortened TTL, there would not be, it would not be obvious that the poisoning had been done. So what the fix for this was that there was a DNS bailiwick check instituted. So in the bailiwick, the query that was made and the answer that came back were compared to see if there was information in the response that really had nothing to do with the query. So in this case, I did the dig at ns1.example.com for www.example.com. And my answer section, yes, sure enough, I get the A record for the example.com server. I get in the authority section, I get the two name servers that are responsible for example.com. And then in my additional section, which is going to contain information regarding other information up in that query, you'll see that I have the ns1.example.com and ns2.example.com A records, so that if anybody needed to go out to those name servers, there would be no need for an additional query. But there was also the entry for www.mybank.com. Now, it's pretty obvious looking at this from our eyeballs that that mybank.com entry has really nothing to do with any of the information in the query or in the response. It has nothing to do with the question that was asked, and therefore it's quite obviously something that we shouldn't trust. So the response here, or the fix for this, was to look at the additional section and see, is the information in this section actually something that should be there? And in this case, this data is not in the bailiwick, and it therefore would not be accepted. So the query would work, the end user would get their answer for www.example.com, but they would not get the information about mybank.com put into the cache of the recursive server. So that is a very specific attack. It was very effective, and as you can see with these very long TTLs, you could do this one time, and then for an extended period, for a day, that information would be in the cache of the ISP's recursive server. So you had to be very careful. You know, obviously, this would be something that you would never notice. The end user, you know, you're in a web browser, or you're in, you know, some other type of application that's doing DNS lookups. You aren't going to notice this information in the additional section, and it just happened. The information, the data was put into the cache, and it was, you know, it was pretty bad. But once it was figured out exactly what was happening, it was very easy to go in and make the change in such a way that out of bailiwick data was no longer allowed, it was not accepted, and it was dropped and not put into the cache. So that was in the 1990s. Moving forward just a little bit to March through June of 2007, there was a researcher named Amit Klein, and he discovered that there were some issues that allowed him to spoof the DNS cache, or information in the cache. And what he discovered was, and so if you're familiar with the DNS protocol, you know that there is a message ID field in the DNS header, and it is 16 bits long. The concept behind this message ID is that a client would send a message off to a server with this message ID. The response that is sent back from the server back to the client has the exact same message ID. So the idea was that as long as you didn't have two servers that somehow managed, or two clients that managed to have the same message ID, there would never be a collision of a response from an upstream server. Well, the idea was that the message ID was going to be randomized. So when you sent off a query, before you actually sent the query, your client would generate a random number, a random 16-bit value, put it into that message ID field, and then send off the query. So the name server that's on the other end, the guy that's responding to this, knows exactly three things about the message or the process, what he needs to do. The first thing that he knows is the source port from which the query came. So if you're sending your message up to this remote server, your source port can be, basically anything from 1024 up if you're a non-privileged process, or anything between 1 and 64K if you are a privileged process. So the source port was known. The message ID was known because that is sent by the client to the upstream server. And then the query itself. So the query obviously is, what am I being asked to get the answer for? www.example.com, a record. So I have the source port, which is on the remote machine. I have the message ID, which is generated by the remote machine, and the query itself, which is again generated by the remote machine. When I respond, my response is going to be sent to the source port with the same message ID, and it's going to include the query, but it's also going to include the answer, whether that is an answer, an actual answer, or some type of error response, NX domain or whatever. So those are the three things that are visible to the name server that's processing the query. So what Amit noticed in 2007 was that the randomizers used in the DNS servers and the clients were not as truly random as they should be. So what he was able to do was recognize the fact that the next message ID could be pre-calculated. So if I knew the query ID of a message that was being processed, then I had a really good idea. I had a good chance of being able to guess the next one. And when I say a good chance, I'm not saying it's a one-to-one thing, or even a 1 to 100 or 1 to 1,000. If they were using even a random number generator, the problem was that some servers didn't use a random number generator. They increment. So when they sent off a query, their first, for example, would be 5. Then we have a come along, and it could possibly be next query would come along, would need to be processed, would need to be sent to the upstream server, and it would be query ID 7. This made it really easy for the bad guy to figure out what the random query ID was, because it really, really wasn't random. But even if it was random, it turned out that there were some implementations of the random number generators that didn't produce really random numbers. So if you knew the previous query ID, you could take a wild guess at what the next query ID was going to be. So in this case, we have basically the same setup. And what would happen is that the evil resolver, the bad guy, would send a query to the ISP's recursive server asking for the mybank.net address record. Well, the pre-calculation would have occurred, and we would guess what the next query IDs were going to be. So we knew that he was either incrementing, or it could possibly be one of the non-truly random number generators. Well, the ISP's recursive server is going to send off that query to the upstream mybank.net server. When that occurs, there is a time lag between the time that that query is sent and the time that that response comes back. Well, Amit's concept was to, while that response or while that query was going from the ISP's recursive server out to the authoritative server for the bank, and then the response was coming back, all of the pre-generated responses would be sent from the evil resolver back to the ISP's recursive server. The pre-calculated IDs would hopefully, in the case hoping that the bad guy was going to win, it would match with the query ID that had been sent from the ISP up to mybank.net, and then was in the response from mybank.net back to the recursive server. If the pre-calculated ID that collided made it to the ISP's recursive server, the resolving DNS server there on the right, if the pre-calculated one with the bad guy's information made it back before the response from the authoritative server, then it would be cached and the response from the bank would be dropped on the floor because there was no, the query that had been made had already been satisfied. The response had been sent, the response had been gotten with the query ID intact, and it would then be put in cache. So in this case, again, if the bad guy, if the evil resolver is able to collide the query ID, then the bad information is put into the cache. If by chance the bank's A record actually got to the recursive server before the bad guy, or if the bad guy didn't actually guess the query ID correctly, then the correct response was put into the cache, and it would then be there for TTL number of seconds. So this attack could only be attempted once every TTL number of seconds when the, if the initial attack failed. So once the mybank.net resource record, the A record, correctly is put into the cache, the bad guy would then have to wait until the TTL ticked down and the data was removed from the cache before they could mount the attack again. So assuming that the cache was poisoned, the unsuspecting end user goes out and does a query for mybank.net address record, gets the information out of the cache, and then gets the bogus response. So the fix for this was a little bit more complicated. The problem obviously was that the query ID of the DNS messages were not truly random. And, you know, cryptography is hard and random numbers are hard. And so getting this right was a little bit more difficult than, you know, saying, hey, this thing's not in bailiwick, let's just drop it on the floor. But the people that were just using the increment by one query ID, they could have done anything and made it more. But the fix was a truly random query ID generator in the DNS servers. So in this case, you needed to go out to all of the recursive servers that were asking or talking to the authoritative servers and make sure that the query IDs were truly randomized. Moving on to March through August of 2008, I was actually working at ISC during this time period, and it was a very interesting and hair-raising period of my work in the DNS atmosphere. Dan Kaminsky recognized that there was a way to spoof DNS server caches even if the query ID was truly random. And the way he did this was that you could go out and you could force a name server, a recursive server, to do a large number of queries against an authoritative server, and therefore it would continually use more and more of these random query IDs, and eventually they would come to you. And I'll show you what that means on these next couple of slides. So the problem was that even if the 16-bit query ID was truly random, a carefully crafted the DNS safety check. So in case I'll show you a slide, these next slides use a set of graphics that I used way back in the early 90s. And what you will see here is this first slide is a slide that actually used during the class, during the DNS Unbind 5-day tutorial. And the reason I show this slide is that this is how I first learned about the Kaminsky attack. So in classic DNS cache poisoning, the attacker would send a query to the caching recursive server. what is the address of www.isc.org? The caching recursive, so at this point, it would send, the attacker would send a large number of responses as if they were coming from the authoritative server to that caching server, hoping that the information that was the query ID was one that matched the query ID that the caching server had sent to the real authoritative server. So in this case, what I was doing was I was trying to poison the cache on the caching recursive server and make it think that www.isc.org A record was 192, 153, 154.4. And so at this point, the victim server, if we had a collision between the query ID and that was used by the caching server to talk to the authoritative and these query responses that I sent back, then we would make a victim of the caching recursive server, and then we would have a victim there on the right-hand side. The end user would get back the information that I wanted, and not the ones that that the actual not the actual one that ISC.org's authoritative servers had. Now, the reason I show you this, because basically it's just a repetition of the previous slide, is the fact that I was giving this presentation in Dallas, Texas, during what I didn't realize at the time was the work on the fixing of the Kaminsky attack. And one of the things that ISC always did was when I was teaching a class, they would send the closest engineer, if possible. I mean, obviously, you know, there were times that I didn't have an engineer in the class with me, but they would send an engineer to sit in on the class. And that was really cool because I could ask questions that I didn't know the answer to. If it was something about the internals, ask the engineer. The engineer could hear the responses, you know, the questions that the people in the class were asking, and we actually made a lot of changes and fixes to bind with an engineer sitting in the class. Well, I was giving this presentation and I was doing this specific slide, and the engineer that was sitting in the classroom was sitting back in the back corner, and he started, you know, making hand signals to me like, stop, please, you know, I'm sweating, you know, I didn't know, you know, if lunch wasn't sitting well with him or what was going on. So I said, okay, let's take a break. And the people in the class kind of wandered away and, you know, went to get coffee or use the restroom or whatever. And I went over to the engineer and said, you know, what's up? And his response was, how much more of this are you going to talk about? Well, I had been using the same slide in my classes for a couple of years, and I just told him, no, this is pretty much it. Why? And his response was, well, yeah, I'm glad that this is all you're going to say. I can't tell you why I'm asking. Well, this engineer and I were good friends. And actually we were, if I remember correctly, in fact, I'm 99% sure, we were actually sharing a hotel room in the place where I was teaching the class. And so I'm sitting there going, gee, you know, that's interesting. So you know, really, you know, tell me what why are you asking? You know, this is, I'm curious now. And he said, well, no, I really can't tell you. It's something I really can't. Please quit asking me. Don't make me, you know, do something I don't want to do. But I will tell you that DNSSEC is going to be really important in about 6 months. Well, I had been teaching this class for a couple of years, and of all the things people did not want to learn about, DNSSEC was right there at the top of the list. At that point, DNSSEC was, it was very difficult to implement because, you know, the command line options, there were, you know, 27 different options that you had to get exactly right. You had to do, you know, everything just perfect or it broke. There was no, you know, there weren't really any recursive servers that were actually doing validation. So even if you deployed it, you know, you weren't getting anything from it. And I had been really excited. You know, when I started at ISC, I was going to be going out there and teaching DNSSEC, and it was going to be really cool, and everybody was going to want to deploy it. And it turned out that nobody wanted to deploy it. So it kind of burst my bubble. And I found it very interesting that this engineer, who I respected very much, was sitting there saying, you know, hey, you know, DNSSEC, it's going to be really important. Well, I laughed at him and said, yeah, whatever. But he went back to corporate and actually went back, and I think he talked to Paul Vixie. And that actually led to a telephone call between all of the support staff and a number of the engineers and Paul himself. And we got the explanation of what the Kaminsky attack actually was. So once I had learned about the Kaminsky attack, and I continued to teach classes, and of course I was really concerned because this vulnerability, when you see it, you'll realize that it was just really, really, really simple to implement the attack. And you know, if you can implement this attack as easily as this could be done, then, you know, as soon as it was known, the script kiddies were going to go crazy, and, you know, the internet was going to change completely. The scope of the internet was going to be drastically modified. So I continued teaching the classes, and of course, I continued using this slide. Wasn't allowed to, of course, talk about the Kaminsky attack. I'm sitting here, you know, with it in the back of my mind going, oh, gee, and I sure wish I could tell you what I really know about this, because things are going to get pretty ugly if you don't upgrade when we say to upgrade. Well, later, after the Kaminsky attack, after the patches had been sent out, and we were pretty sure that everything was about as well covered as we could, I was actually looking at getting a security clearance. We have a number of customers who, you know, it would be nice to actually be able to teach on their campus instead of having to teach, you know, at a hotel somewhere in another town or across town. And I was talking to the folks that were, you know, working with me on the possibility of getting the clearance. And I, you know, started talking about, you know, what kind of information, you know, does when you have a security clearance, the information that you know actually modifies the places that you're allowed to go. Well, one of the places that I was teaching a class was in Australia, and my return path was from Australia to Indonesia, Indonesia to Moscow, Moscow to Houston, and then Houston back to Raleigh-Durham, where I was living at the time. And it was very concerning to the investigator when I said that, yeah, I had actually known about the Kaminsky attack. And he said, you know, if you had known about that attack and known it in the detail that you knew, and if you had known, and if you had had a security clearance, you would not have been allowed to travel to Russia. It was at a security clearance level that if I had had a security clearance, it would not have allowed me to make the travel plans in the same direction that I had. Very interesting, and something that I had not even thought about. And it shows you the level of concern that was around the Kaminsky attack. So let's move on now to see what the Kaminsky NS attack actually looks like. So again, we have the same basic configuration. We have the attacker, we have the caching recursive server, and we have the intended victim up there on the right-hand side. Well, in this case, the attack is a little bit different because instead of asking for the thing that we're trying to take over, so instead of asking for www.isc.org, the attacker would send a query for some random label. And it would actually want to be something that does not exist in the isc.org domain. So they would ask for randomstring.isc.org. And what was discovered was that when a random query like this occurred to a caching recursive server, the attacker could send around 200 responses back to the caching recursive server before the authoritative server was able to respond with the NX domain that was obviously the correct answer, because randomstring.isc.org doesn't exist. So the fact that we can send about 200 responses before that NX domain gets there allows us to say, well, let's send 200 query IDs in the case, that one of those 200 query IDs just happens to be the one that the caching recursive server used talking to the authoritative. Well, in this attack, it's pretty nifty, because since you're asking for something that is a randomstring.isc.org, you send back these 200 responses. If you don't hit it, you just change the random string, do a different query.isc.org. The caching recursive server says, hey, I don't know what that one is either, sends the query off to the authoritative server, and the attacker gets to send another 200 responses. Well, okay, that's great, but why do we have to worry about, the query ID? It's random, it's truly random. The neat thing is, if you take the range of the 16-bit value and you split it across 200, divide it by 200. We'll see in just a second why that's a very important number, but let me show you here the responses that you're sending. We are not trying to get www.isc.org. What we're going to do is, in our response, our authority section is going to have in it an NS record for a name server that is not the one served that serves isc.org. So in this case, the randomstring.isc.org name server is going to be ns1.mydomain.com, and mydomain.com, that ns1 server, is a server that is owned by the bad guy. So the bad guy is able to set up a server that is going to respond to queries for isc.org. And okay, that's really fantastic, but now we have a random string where the NS record points back to something that we own. So what? Big deal. Well, again, since the random string is different every time, we don't have to worry about anything being in the cache. We can fire this, we can pull the trigger on this query as often as we want until we get it to hit, until we are actually able to get the response or we're able to match the query ID that the caching recursive server used with the one that we generated. Well, I mentioned earlier, so the attacker is going to continue until they get one that hits. So I mentioned earlier that we're going to take the 16-bit value. So it has a total of 64K possible options. We're going to divide that by 200. And that's how many queries or how many responses we're able to send back that are going to get to the caching server before the actual NX domain. Well, I just keep sending the same 200 over and over. And every 327th query that I send is guaranteed to fall within that 200 block of query IDs. So if I use the query IDs 1 through 200, then I know that within 327 of my random thing.isc.orgs, I'm going to match up with the query ID. Now, okay, so what? I now have this NS record for randomstring.isc.org pointing to someplace that the bad guy owns. Well, the nifty thing about this from the bad guy's perspective is that he now owns isc.org, because any query that is being sent to that caching recursive server for anything .isc.org that isn't already in the cache, it's going to go out to the ns1.mydomain.com server for the answer. The bad guy sets up his server at ns1.mydomain.com, and the answer that he gives back is whatever he wants, anywhere within isc.org. So it's not just attacking www.isc.org, it's also attacking vpn endpoint.isc.org, It's also, taking over secure PayPal interface.isc.org. Anything within isc.org is now taken over by the bad guy. So this is a very interesting attack because there's nothing at all that the authoritative server can do about this. All the authoritative server can do is respond to the random queries that these caching recursive servers are sending back. There's nothing that they can do to guess what the next random query is going to be from the attacker. Once the NS records are in place on the caching recursive server, there's nothing that the authoritative server can do to get them out of there. So this was a very interesting attack. It was a very toxic attack. It was a very clever attack, and it worked very well. So at this point, since I'm replacing the NS records for isc.org, I own the entire domain. The victim server, the caching recursive server, now asks ns1.mydomain.com for anything that is in the domain isc.org. So in this case, the answer that's given back, obviously it's not the NS record, but it is what is responded to by the name server at ns1.mydomain.com. Now that's really cool. That's a really nifty attack. You can actually do this with a shell script and netcat from the bad guy's perspective. And even more amazing is that you're not taking over just, a second level domain. You're not taking over just isc.org. You could actually take over a top level domain. You could use this exact same attack to take over com, net, org. It's terrifying. And everybody except for one name server was vulnerable. Dan Bernstein with TinyDNS actually did not allow this. The NS records that came from, that we were in the original query were the ones that were kept in cache. He did not overwrite the cache with the information that was in the attacker's responses. But all of the other name servers on the planet were vulnerable to this. So this was a very ugly time because the vulnerability was so simple to do, and the fix for it was going to be so obvious that if one name server vendor went in and made the change, provided the fix, then everybody in the world that was actually actively looking at, hey, look, Bind just released a patch that does this. What could possibly be the reason for that? Well, this is something that had to be coordinated. The patch for this was released by Microsoft, Cisco, ISC, Nominum, Sun, all of the Linux distributions, all on the same day and at the same time. This was a crazy amount of effort, and it really paid off because before any large-scale attacks were able to be mounted, most of the name server operators, the large server operators, were able to put the patch in place. So in this case, again, we have the victim client who doesn't have any idea what just happened. So again, the attacker tries to overwrite or place the NS records in the cache by doing a query or providing an answer for randomstring.mybank.com, where the authority section has in it the NS records and the additional section that has in it whatever is wanting to be used by the bad guy. So this was a difficult patch, or this was a difficult fix, because it was something that was actually in the protocol. It was a protocol break, not just an implementation failure. So what needed to be done here was that we needed to have additional randomization in the query and the response. And in this case, what was done was that UDP source port randomization was put into place. So prior to this, there were most name servers, and in fact, you can still find in a lot of I've seen, in fact, even recently, I've seen where name servers has been locked down to use the outbound port 53 because that's the one that our firewall allows DNS through. Well, when you lock down to port 53, then you're vulnerable to the Kaminsky attack. So the way that this was implemented, the fix was to randomize that source port. And there were a number of things that actually caused. There were problems that caused. There were some firewalls that did not appreciate very much the sudden new amount of traffic. There was an outbound port coming from some random port on this name server going out to port 53 on a remote, and then we had to keep state to make sure that the response was actually allowed back through the firewall. And so the state tables on a lot of firewalls weren't able to handle it. Some of the firewalls and small office, home office devices actually undid the randomization. So if you had a bind server or another name server inside that was randomizing the source port, the firewall that was in place would go, hey, I recognize that this is going out to a port 53, so I know it's DNS, so I'm gonna squash that randomized port number, and I'm just gonna send it out on whatever port it was configured to use. Now, there were some other tricks that were used, one of them being the use of, it was called OX20, and that is the offset between a lowercase letter in the ASCII character set and an uppercase letter in the ASCII character set. So you could do a query for www.isc.org, but the outbound query would have lowercase w, uppercase w, lowercase w.isc.org. The response from the remote would also have to have the exact same lower and uppercase combination, and the attacker would never be able to guess what the capitalization was. The problem with that was that there were name servers out in the world that would fix the case of the response, and it would lowercase everything, and then the guy that's on the inside trying to do this comparison between the upper and lowercase www and the response that was all lowercase, that would fail miserably. So the only truly good fix was to actually do source port randomization. And even that wasn't a true fix, because statistically you can still guess the port number because it's between 1 and 64K, and you can still guess the query ID because again it's between 0 and 64K. And so all this did was really extend the amount of time that it took to do this attack, and it really made it an unusable attack because the length of time that it took was tremendously long. The one and only true fix was to deploy and use DNSSEC. So this was the thing that actually pushed a lot of DNSSEC deployment. The U.S. Department of it's the OMB, the Office of Management. No, that's not right. Anyway, the OMB came down and said, you are going to do DNSSEC in .gov. Of course, they didn't say anything about it being tied to the Kaminsky attack, but it was in a very similar time frame. So I kind of put one and one together, and I'm guessing that the Kaminsky attack was a large push for that. So again, the patch only raised the bar for the attacker from about 10 seconds, which you could do with the 200 queries and 200 responses per query, to about 10 hours. But this 10 hours was really not realistic because it was on a server that was basically a back-to-back gigabit network where the attacker and the recursive server were both on the same network. It really wasn't, it was statistically possible, but not realistically possible. So the big thing here was after you configured and updated your DNS servers, you had to still make sure that the source ports were truly randomized. As I said earlier, some of the firewalls or NAT devices undid the randomization. So the only one real fix that was available and still remains available is DNSSEC. So to talk a little bit about some other attacks that didn't have any specific users behind them, any names that I could attach. Obviously, we have man-in-the-middle attacks. And in this case, the DNS messages can easily be intercepted en route and either changed, altered, dropped on the floor, done something to, and then sent back to the client. And again, the normal user at the end of the line would never notice. Man-in-the-middle attacks are very, very easy if they are, if you're using plain DNS with no DNSSEC, and obviously without, today we would say DOH or DOT. The issue here is that most DNS is done over UDP. And that means that it's stateless. There's no connection built up. There's no, hi, I am talking to you. I know I'm talking to the right person on the other end. It's basically fire and forget. I send the message and then I hang around waiting to see if I get a response. Well, if the bad guy is somewhere on the path between me as the client and the upstream server, whether that client is a recursive server or an end user, if somebody is on the path and they're able to snag port 53 traffic, then they can modify that traffic and send it back in any way that they want. Every DNS packet, both the query and the answer, contain the full header and the query section. So as the query goes out, and of course this is not true anymore quite so much with QName minimization, if you have deployed that, but we're not going to talk too much about that. In fact, this is the only time I'm going to mention it. QName minimization, you don't have the full headers or you don't have the full query in every outbound query. The bad guy is very easily able to see what's in the query going out. They can modify the response. They could actually drop the packet on the ground, forge their own response and send it back, and the end client would be none the wiser. Betrayal by a trusted name server. So I know that I am talking to the correct name server, and so the DNS clients trust that local server. Unfortunately, some of the servers are not so trustworthy. If you consider when you go to a hotel and you attach to their wireless network or even their wired network, if any of those still exist, and you configure your client using DHCP, if you're not very careful, if you're not, using a VPN solution or some other hardened mechanism where you don't get a name server that you're not familiar with, that you don't trust, you're now at the mercy of whoever runs the DNS server to which you're sending your queries. So, an attacker can install a rogue DHCP server and hand out configuration pointing to a pirate DNS server. That was a really neat little attack that I saw pulled off. You somehow managed to get into a corporate building. You're able to get onto their network, the wired network. You're able to get into a closet somewhere. You put in a small server that is acting as a DHCP server. It gives back answers that look exactly like the ones that the real DHCP server is handing back, except that it is using a different DNS server. So that's a pretty nifty little attack, and you have to be on the wire to get away with that one. So if you have good physical security, you're in good shape, but physical security is also pretty hard. And then the example that I gave earlier, an attacker might be able to take over an internal or external caching DNS server, altering the data without anybody noticing. So, the people that work in a hotel, they are not the tech support guys. They don't really know much about the network, I have discovered in trying to deal with, problems on their networks. It would not be too hard for a bad actor to get in and do something, putting in a server that isn't the right one. And obviously viruses or spyware are able to alter the local resolver configuration. Your client is not using the server provided by DHCP. It's using something that, that game that got installed. It overwrites your name server configure, your resolver configuration. Even so, as much as putting a DNS server locally on the client. And that local DNS server, our machines these days are so powerful that, a small, lightweight DNS server might not even be noticed if it was running on your local machine. And then, of course, there are attacks on authoritative data. If there is a DNS server out there that somehow the bad actor is able to get onto, they're able to log onto the machine, or somehow able to get access to the disk drives, or maybe it's a NFS mount or who knows what, any exploit of a security issue on those servers that allows the user to get onto the machine with privileges to actually be able to write the data that the name server on that machine is using, it's going to be a bad day. If there are security issues in the operating system, in the DNS server software itself, or in any other network-facing software on that system, you run the risk of having somebody get in, modify the data on the authoritative server, and then you don't even have to worry about being on the wire or spoofing anything. You just modify it on the authoritative server and you take them over. And then, of course, we have the denial of service issues with DNS. Overwhelming a DNS server, lots and lots of queries, or queries for an A record where the response is, a 4K blob of A records. Lots and lots of things. Mini zone transfer requests. If you're able to spoof a secondary server and have it do lots and lots of zone transfers from a primary. And then, of course, using DNS servers as an amplifier for a denial of service attack. You send a very tiny query, just a standard A record query, but instead of your actual IP address, you send in the UDP53 packet the source address being the person that you are wanting to attack. And then the remote server says, oh, hey, sure, I can send that response to that remote server. And congratulations, you are now overwhelming somebody that you have absolutely nothing to do with. BCP38, if you don't do it, if you don't know what it is, go out and do a search. BCP38, make sure you filter ingress and egress from your networks. Distributed denial of service attacks. Lots of servers serving recursive clients to queries to any client. Well, we have some good ones now that are recursive, open recursive servers on purpose. For example, 8.8.8.8, 4.4.4.4, Quad 9, the all ones. All of these servers are able to provide answers back. In 2013, there were 28 million problematic DNS servers on the internet. Open Resolver project, I don't think it's actually being maintained anymore. I think they gave up in defeat after seeing 28 million open recursive servers out in the world. Distributed attacks, behavior can be exploited again by launching a query for a simple A record against a bunch of open DNS servers. You send the source address as the target of your attack. All of those open recursive servers send even a very small packet back to the spoofed source address, and the good guy, the victim, is overwhelmed because of the amount of incoming traffic. So with that, I see that wow, it is 1 minute until the hour. So that would wrap it up for week number 1. Week number 2 will be, next week. So I am going to blank my screen now. I'm going to turn off the share and see if there are any questions or anything that I need to